Yeah, thanks, Avi, for giving me this chance. I know about this place since I was 12 years old, and I was just telling him means a lot. So today we are going to talk about locally repairable code, storage capacity, and index coding. So all of this topic, at least two of them, as I know, locally repairable codes and index coding are introduced. These notions are introduced by theoretical computer scientists, but I don't think there are enough TCS people that are working on these topics. There are some, and they did really good results. They came up with really good results. But in the information theory community, these were pretty hot topics, and there are plenty of papers recently. So I will just, for 2 minutes, I will tell you what codes are, but I assume all of you know from the so what is a code? A code is just a subset of vectors, a collection of vectors over some alphabet Q, and we denote by K throughout this talk. The dimension of the code, which is by slight abuse of notation, is log of whatever is the size of the alphabet of C. So if this Q to the power n, if this is somehow identified with fq to the power n, and if C is a linear subspace, then this is the dimension of that subspace. But we will talk about general nonlinear code, and we will still use the term dimension, where we will just mean this. Now, this is not an arbitrary set of vectors. It is over a matrix space. It is equipped with a distance, usually the Hamming distance, and we define the minimum distance of the code as the minimum pairwise Hamming distance. So this is the Hamming distance between any two code words or vectors in this collection. With that, we have, and for linear code, the minimum distance is also the minimum Hamming weight, or the number of non-zero entries in any code word. And to denote a code, we write nkd. So this is the length of the code, or the size of the vector, length of the vectors that are in this collection. This is the dimension, and this is the minimum distance. This is for general nonlinear code over a query alphabet. If it is a linear code, then we denote it with this square bracket over there. Okay, so this is for nonlinear. This is for linear. Now, our objective is to come up with the largest such code with a given minimum. So we can define a Q in D to be the largest size of a code of length and distance, or minimum distance D. Okay. This K by n, the dimension divided by normalized with length, is called the rate of the code. So the highest possible rate of the code is going to be log QAQ ND. And then we normalize it, suppose, by n. So this is the largest possible rate of an error correcting code. It turns out that it is good idea to look at when the distance of the code varies linearly with some delta, and we say that if this goes to some limit, suppose that limit be r delta. Now it is not known, so rq delta. So if we just omit this q, that means it's a binary alphabet, so we just have binary codes. So if this goes to any limit, is not absolutely known. So it's known whether this goes to a limit, but there are upper and lower bound that are known, and we will prove some of this upper bound. So the upper bound here means the converse result, or the impossibility result, and lower bound as opposed to what is usual in TCS. So it's known that there exist codes. So now I'm dropping this Q and I'm talking about only binary alphabet. So easily can be extended to. So this is greater than equals to 1 minus h delta, where h is the binary entropy function defined by, so h of x is minus x log x minus 1 minus x log 1 minus x. So this is called the GV bound. This is not very difficult to prove. You can show that some such codes exist by just greedily choosing code words that are distance d apart, or you can just randomly choose a bunch of code words and show that just by probabilistic methods there exists a code with this. Now this bound can be improved when the alphabet size q is greater than 49. I think so. There is so you can have an improved bound which is r q delta is greater than equals to 1 minus delta minus 1 over square root of q minus 1. So this is possible. So this is an improvement over this only when q is greater than equal to 49. This is by using something called algebraic geometric codes by Fassmann, Vladut, and Zink came up with this result in early 80s. Now when q is greater than n, so your alphabet size is large, say greater than equal to n, then it's exactly known what is the, so there is this bound called singleton bound that can be matched. So this is the singleton bound. Distance has to be less than equals to n minus k plus 1. Again, this bound is really easy to prove. You just list all of the code words, and then you know that even if you puncture these code words in d minus 1 location, so if you just erase d minus 1 coordinates, the code word still has to be different, distinct, and that gives you this bound. So this bound is tight only for the case of q greater than equal to n. It has been shown, and there are some conjectures around this value which are called MDS conjecture. The codes that achieve this bound are called MDS codes, or maximum distance separable codes. Right, and this gives us our q delta to be 1 minus delta. So ReedSolomon code achieves this bound. We will again make use of this bounds code. They achieve this. Okay, so one other thing. So I was going. So these are pretty common. I dropped something there. But these are pretty well-known results. Everyone knows about them. So the only one other things that would probably be a repetition to all of you is some upper bound on this, impossible result on this, that so we know that r delta is always less than equals to h of half minus right. So this is called the first MRRW bound, and unlike this these other bounds that I talked about, except for this one, this is quite non-trivial. This cannot be derived by very simple elementary method. You need something. Although we will look at the proof of at least this first MRRW bound and see get some intuition behind it. However, this is not very simple. To give the complete proof, I will have to spend a lot of time. I will not do that. So there is a slightly tighter bound than this, which is called the second MRRW bound. And off the top of my head, so that's a slightly complicated expression, but we are not going to go there. So this is not the tightest possible. There is one other bound which is slightly tightest, which is second MRRW. So to summarize, if you just draw this r delta against delta, it turns out something like this. So delta equals to half. Here r delta turns to be 0. So this is the GV bound, and the MRRW. So this is MRRW. There is a pretty big gap between them, and like one of the classical questions of coding theory is either to push this sorry, it's the lower and upper thing. So this is the MR W, which is the upper bound. This is the GV bound. Either to push up the GV bound a little bit or to push down the MRW bound a little bit. Both of them is recognized to be significantly difficult task. Okay, now that we have all the basics, what are locally repairable codes? So this notion came from some real practical application in distributed storage. So suppose you have two codes, and one is called a parity check code, and another one is a repetition code. So let me list the code words for binary codes. So this is, and so these are the code words. So it has 4 code words: 000, 011, 101, and 110. And then this guy has 4 code words as well, which is 00, 00, 01, 01. 10, 10, 11, 11. So this is a parity check code. This is a repetition code. Now, this code is definitely better than this code according to the notions that we have set, because this has this is achieving a smaller length than this, and they both have minimum distance 2. So if there is any one symbol which is lost, you can figure it out. So it can correct, in other words, one erasure. So if you just erase one of the bits, I can still figure out what this bit was, because I will just XOR these two things, right? In this case, it can do the same thing. If there is any one symbol is lost, it can figure out it from this. So suppose if this is lost, you still know this is 0, because you can just look at this. But it turns out that in this distributed storage industry, they still prefer to use this type of repetition instead of this, because of the following reason: that if you want to recover any of the bits that are lost in this code, you have to go to 2 other bits, right? And here, if you are to recover any of the bits that is lost, you have to just go to 1 other bit. So that is called the locality of code word symbol, and then you can just maximize it for all of the coordinates. So the locality of this guy is 2, and the locality of this guy is 1. And if you are storing some information in a distributed manner, if your locality is small, that's desirable, because then you don't have to go to some other place to recover this, right? You have to go to less number of other places. So we introduce another parameter, which is R, the locality. So now we have N, K, D, R, and this was introduced by Gopalan, Huang, Simitsi, and Yekanin at Microsoft Research around 2010, 2011. Okay, so you have a new parameter called locality. And any code that has a small constant locality. So anytime we talk about a code family, we are basically talking about N, K, N, D, and something like this. So, but we want this locality to be constant. So we want, if that happens, then this family is called locally recoverable or locally repairable.
So, but you look only at erasures now, or you look only at erasures now, or not erasures?
I've just looked at erasures.
Erasures.
Yes, only erasures.
So that's how it is different from locally correctable codes?
Yes. In locally correctable codes, this is just a property of the codes, and we are not talking about error correction here. So in locally correctable code, you have a bunch of errors, and then each of the coordinates can be corrected by accessing only few other bits.
Yeah, so now each of the coordinates is a function of some R.
Yes,
Not
yes.
necessarily random, not necessarily.
Not necessarily.
Exist,
There
as
exists.
a determinant.
Exactly.
The difference is huge. I mean, here you have one local constraint per coordinate, and locally correctable, there's a linear number of them.
Yes.
That's
They
right.
spread over
So this is much like in some sense this is much easier. So there, so the domain. So for locally correctable codes to show that you have a constant rate is a challenge. Like so you have to overcome. Yeah.
You can't
That's
have
impossible. Right. But here your regime is completely different. That's why I introduced. So you basically want to show that how far away you are from this bound if you have these constraints.
Yeah, and the D means that you always, if you erase D,
You can still.
function of D here.
So
Function of D here is that you can recover any coordinates from R others after some D were erased.
no, there is no such
What is
constraint.
what is the value of D? What does
It says that your code still has this minimum distance. So in the case of catastrophe, you will still be able to recover it. But on top of that, you just have this extra constraint that each coordinate is function of our other coordinates.
There are two independent.
They are two independent constraints, and the reason they put this forward is because although you want to prepare, use a good code to prepare for catastrophe, most often you just have one error or two errors in the storage system. Like that's more day-to-day thing. In that cases, you don't have to go. But suppose there is a complete shutdown, like a bunch of them fails, then you have to basically shut down everything and recover. And
So the parameter R, is there another parameter that says how many errors can you recover from locally, or is it like one or two?
no, well, you can have more. Yeah, you can have one other parameter that says that okay. So in case of any 2 failures or any 3 failures, you have to go to only few other nodes and recover it. But we are just basically looking at this one coordinate thing.
Here you can have one coordinate error, and so then this if you only have one R tuple that you can recover from, there can be an error there, right? So
Oh no, it's not in the presence of
Every coordinate can be recovered from some other coordinate.
without noise.
without noise.
Without noise. Okay.
Without noise, every coordinate can be recovered. So if there is only one failure, you don't basically decode the entire code.
Right.
You can do this simple thing. Well, if there are more than one, you don't know. Then you have to do the decoding of the code. Okay. Right. So that's locally repairable. And then the question is, what would be how the bounds that I have just mentioned here will change if you have this new extra thing called local repairability.
For those who don't know, this construction apparently saved Microsoft some 100 million.
Right. And then they close this lab as well.
That's a reward to the inventor.
Yes. I think as a reward, they still go, like at least Sergey still has his job there but not in that theory. Yeah, it certainly is not what it used to be. Yes, so they came up with some very simple schemes that are implementable in this real system. Those are not really fancy, but that has this local repair property. So before that, they were using some BCH code or something, and every time there is one failure, they have to decode the entire code, and that's how the savings came. Right. So this is locally repairable, and in this same paper, they gave a bound on the minimum distance. It says d less than equals to n minus k over r plus 2. So this is very much, if you look at this is something. Where is where is the singleton bound? Yeah, so this is very much like this with just this extra term over here. So that's the penalty for having locality. Okay, but as in the case of singleton bound, this bound is good only for large sized alphabets. So q has to be greater than n. So then subsequently it has been, I will show you the proof of this bound. It will come. So subsequently, it's not very difficult. It's just a modification of that bound, the singleton bound proof. It was also shown to be tight. So there exists a family of code for which you can achieve this, and that is by Varg and Tamo, 2014. The way they do it is a modification of the ReedSolomon construction. So for that bound, so ReedSolomon codes are actually evaluation of polynomials. So you take the collection of polynomials of degree at most k, and then you evaluate those polynomials over n points. And if you are over a field of size q, n has to be less than q. That's why the size of the alphabet has to be greater than n. Right? So and ReedSolomon codes are, so suppose you have a it's a bad example, but suppose you have a polynomial like this. So ReedSolomon codes are just evaluation of those polynomials over n points. And then Tamo and Varg, that construction was saying that maybe there is a lower degree polynomial like this that intersect this polynomial at these 3 points. And now to recover these 3 points, you don't have to basically evaluate the entire polynomial. You can just evaluate this low degree polynomials. So instead of evaluating all polynomials of degree k, they are basically looking at a subset of polynomials that can be decomposed into this low degree polynomials. That's the main idea. Product of low degree. Exactly, and that was the construction. So once you know it, it's simple, but it's still it's a really nice idea. So that achieves this bound.
So again, the code is just evaluate all polynomials which are product of which have factors of degree r.
Which are factors of degree r, and then there is a little more in terms of choosing the evaluation points. You cannot evaluate them on all of the points of the finite field anymore. You have to restrict yourself to a subset, which comes from some technical constraints. So that was their construction that achieves that bound. However, nothing conclusive is known when q is less than n. Which is suppose binary codes, there is not much is known. Okay, so what we are going to talk for the next some time is what are the best bounds for q less than n, and we will concentrate on binary, because if you can solve binary is the most difficult case. If you can solve that, that would be good. Okay, so we are in this regime. So in this regime, so there is a simple idea. So it's the shortening a bound that can be used, that uses this MRW bound as a black box, or any other bound as a black box. The shortening idea is following. So suppose you have a locally repairable code. Its parameters are n, k, d, and r, possibly nonlinear. Now, suppose for coordinate I, Ri is the recovery set. So you go to, see, basically xi is a deterministic function of x Ri, if x denotes the variable that are there in the coordinates. Okay, so Ri is called the recovery set. Let's look at, so suppose I pick t coordinates, I going from 1 to t, and take union of those coordinates, and also take union of their recovery sets. Okay, So I know that this is right. So let's call this some IT. I know that if I restrict the code to this coordinates, then the total number of code words that I can total number of vectors that I will find is not so. Yeah. So what I'm trying to say is, suppose I restrict the code in this coordinates. That means I'm looking at the projection over here and looking at this size. So this is always less than, say, if it is q, then q to the power. It's probably easier to have the tr as opposed to tr plus 1, right? So just to make this completely rigorous, some of the recovery set may overlap, right? So what we will do is we'll just add some, say, so whatever is t times r plus 1 minus size of it. Suppose we just add arbitrary this many coordinates to your set and come up with something like a jt. Okay, so you append those coordinates to this set to get something jt. So this is jt. And the size of jt is going to be less than equals to q to the power tr, because there are t coordinates that can be deterministically found by looking at the other coordinates. However, the total number of coordinates that you are looking for, so the size of jt is t r plus 1, right? Now, if you restrict jt to this, you have this many different vectors. So think, like, without loss of generality, that this jt is the prefix of your code word. Suppose these are the first t times r plus 1 coordinates of your code word. Now there are this many, at most this many prefixes, and there are q to the power k code words. So if you just do a PGN holding, there has to be one prefix that is that supports this many code words, right? So all of them has same prefix, right? So in other words, you found a code has length n minus whatever is the size of jt. So that's t times r plus 1. And it has, so for those codes, the minimum distance is d, right? Because the distance of the code was d, and I just am looking at the same prefix. So therefore, the rest of the part is has minimum distance d. So k minus tr, which is the dimension of this code, must be less than equal to the optimal possible dimension of a code of this length and this distance, right? So you can write k to be less than equal to, now you can optimize over t, whatever is the best possible t you can choose. You minimize over all t. You have tr plus kopj n minus tr plus 1 d. Right? Okay, so yeah, so this was a bound that by. So we did few years ago. This is 2013. So this is a very simple argument, and now we can just use this. We have many bounds that we know holds for binary code. We can just plug in those bounds to get the bounds on locally repairable code. It's a really simple argument, but it gives bound of this kind. So suppose you probably need this. So it first of all, it shows that you don't at rate. So this is delta. So at delta 0, your rate has to be r over r plus 1. So it cannot go beyond that. And at delta, it again comes to delta equals to half. So if you plug in MRW bound, you will get something like this.
So this is 1/2.
This is half. And this is r over r plus 1. So if we are really looking at small locality like r equals to 2, then it will start from 2 over 3 instead of being from 1. Right? So that's the bound. So this is this thing with MRW, suppose. Now we also know, so this is also good in the regime of small locality when your rate is really small, or you are close to this delta equals to half. So if you take first order Reed-Muller code or simplex codes, so that will have locality 2. Why it would have locality 2? Because simplex codes or the first shortened first order Reed-Muller codes are dual of Hamming codes. If you look at the parity check matrix of the Hamming code, that is the generator matrix of this code. But in the parity check matrix of Hamming code, so if you just add two of the columns, you will get a third column, right? So any column can be decomposed into sum of two others. Therefore, the locality of first order Reed-Muller code is 2. And in this bound, if you just so there is this bound called Plotkin bound. So if you just plug in that bound, you will basically get back a Plotkin bound with r equals to 2. You get back the parameters of simplex code or first order Reed-Muller codes. So they achieve this bound, but for really low rate. Okay. So but we are interested in the asymptotics, which is we want to compare like in this regime when d equals to delta n. Right. So in both of these ends, we have constructions that basically matches this bound. But in the middle, we do not have anything. So in the middle, what is the best we can do? We can try to get something which is like a GV bound. So one way of proving GV bound is to, as I said, is randomly pick up code words. So we can just do the same thing. We can just pick up code words. So suppose but in this way. So code words of length. So okay, so these bits are all randomly picked, and then I add an parity. So there are n over r plus 1 different blocks that we have here. For each of the block, I'm picking up r random bits, adding a parity. So this is by definition, it's a locally repairable code, and we can try to figure out what is the minimum distance of this code, which is not very difficult to do, just by using simple probabilistic methods again. We can choose this code, these blocks as code words of some linear codes over 2 to the alphabet size 2 to the power r, and then like expand them naturally in binary, and then add the parity as well. Okay, so that the overall codes remain linear, and we basically get the same bound. It turns out that that bound is below over here, and this is the GV, and you would say, okay, this is natural that there is a gap between these two, because anyway there was a gap between GV and MRW. So if we just assume a GV conjecture over here, like for this, is that
better upper bound there,
right? So suppose
the GV bounds are
GV boundary is tight. Suppose that was the case, then so in other words, suppose there is no gap over here.
no gap because the upper bound went to the lower bound.
Because the upper bound went to the lower bound. The lower bound is tight. So if you assume that, it turns out then there is still a gap over here. So this is this shortening GV conjecture. So there is still a gap. So either this shortening bound, this is not doing the optimal, or this construction is not optimal.
It's unlikely this is doing this optimal thing because it's sort of ordered. I mean, it just
right. So what we are next trying to do is to improve this thing, because that seems like the easier thing to approach.
So where are you going? You are going to show a better
We am going to
construction that will move the curve all the way to the GB?
No. So the best that we could do now is to just move it a little below, like that, like just little, and that too not for general codes, for linear codes. So for general nonlinear codes, this is actually open. So we are just here. So I told you what the results are. There is nothing much that we can do. Right. So it's probably worth mentioning that there is one more result over here in this Gopal and Huang this paper, and that says that if there is any code that achieve this bound, code family that achieve this bound, then the repair groups are all disjoint, has to be disjoint. And what is a repair group? So I and Ri commonly they together form a repair group. So you see so if you just use one parity for all the coordinates of Ri and Ri, then you can recover every coordinate in that group just by solving that parity. Right? So that's a repair group, and it says that if you are to achieve this, then these repair groups have to be all disjoint. That was proved for linear in this paper. For linear, that was not that difficult, but later Iekhanin, so Forbes and Iekhanin, they proved that for nonlinear codes also this is what they call structured theorem. This structured theorem has to be valid. So that's.
So that means that it just it's
Yeah.
sort of without loss of generality, the construction you showed over there. That's the only way
Not for binary though. So they showed
structure theorem is not for binary.
not for binary. So there is no structured theorem for binary. So I don't know whether this is the optimal thing to do or not. By the way, you can easily obtain this bound, just substitute here the singleton bound. You'll get back that bound. Okay. So for larger alphabet, everything is fine. You are in place. For binary, none of these results are known.
So can you say again why they have to be disjoint? So an element can only belong to a single recovery group?
Yeah, I mean it's not there has to be, if you are to achieve this bound, for example, in this Bark-Tamo construction, they are therefore starting with this type of assumption that every repair group has to be disjoint. That makes their life much easier because they know that this will take them to. But it needs a proof. It needs a proof. It's not that straightforward. Okay, so let's see. So what I will tell you next is how do we move this bound a little over this direction. And actually we can move it, but that's really very slight improvement and restricted to improvement on this shortening with MRRW. Now you can assume that GV conjecture is true, and maybe you try to move this thing a little below there. I don't know how to do that as well. And that is it is restricted to two cases. One is it has to be linear. Then we get a slight improvement. We get even more improvement if we assume the disjoint repair group thing. Okay, so slight improvement here, a palpable improvement over here. And the way we improve it is the main idea is that comes from an improvement of the rate. So it comes from an improved bound on the rate versus relative distance for LDPC codes. That's by Samonosky and Iceland and Samonosky. So the idea is due to Iceland. 2014. So they do it for LDPC code. You can adopt the same idea for this codes. Right. So there are a few things that. So first of all, we can see that if this code is, we can translate this bound for the case of linear code, and then this thing would be. So if we have linear over here, then this thing can be linear, because instead of just doing pigeonholing, we can basically show that that prefix without loss of generality is all 0. Yeah, and then the rest of the code remains linear. So that's one observation. And then there is another observation for the case of linear, which is that if you have a linear code and you have this recovery functions, all the recovery functions have to, like, without loss of generality, you can take them to be linear. I mean, if not, you can.
What means the recovery? Oh, the functions.
The functions are linear over that field. I mean, these are like simple exercises that you that you can do. That means that if you look at the parity check matrix of the linear code, by the way, we are concentrating now on linear code because we don't know a way to improve that bound for general nonlinear code. Just to remind you, so we are talking only about linear code. So in the parity check matrix of the linear code, there will be some rows that has weight r plus, right? Because those are the linear functions that you can use to compute. So there, plus this r plus 1 weight parities must cover all of the coordinates, all of the n coordinates. So this constraints, we know these two things. So knowing these two things, we will be able to improve. So the tool that we use is like the lemma, or the, it's actually basically proving everything. So it says that, okay, so you can define for any code C. So before I define, so any code C, if it is a linear code, it has a dual code. Dual code is just the orthogonal subspace of this linear subspace. And you can define something called a coset leader graph. Graph of this dual code. So the vertices are all the coset of this. So you, and then you put edges if any two cosets are Hamming distance 1 apart. So if there are two,
the cosets are a one-to-one correspondence to elements of the code, right?
Cosets.
Number of cosets of C pair.
Right, right.
Are the same, is the same size, or they are one-to-one correspondence.
One-to-one correspond. Yes, yes.
There are shifts of C by code words.
They're right.
There's shifts of C per by code words.
That's true. Yes, yeah.
So it's, we can think of the vertices as elements of C.
It's better if you think the vertices as the rows of the, as the columns of the parity check matrix of C. Yes.
What's the number of vertices?
Oh no, sorry. The number of vertices. Sorry, yeah, that's my mistake. It's generated by. So you basically think of the Kelly graph, with the generators being the columns of the parity check matrix of C. So this, you can show these two are isomorphic. So the number of vertices is the number of cosets of C dual, which is the size of C. Yeah. Yes. Yes. And if you will have edges, if any two cosets are distance 1 from each other, which is Hamming distance 1 from each other. That means, like, in the two cosets there are two vectors that are only distance 1 apart. By distance between two cosets, I mean the minimum distance over all pairs of that cosets. So if you have that, there is this lemma by, so this is actually Friedman. I don't know if there isn't this E. I think there is this E and Tillich. This is the generalized Alon-Bopana bound, and it says that the size of C is going to be less than equal to 2 to the power little o of n, where tau is defined to be half minus square root of delta times 1 minus delta, and b tau n is the set of all coset leaders. By coset leader, we mean the minimum weight vector in that coset. Set of all coset leaders that are within their leaders of weight less than equals to tau n. So this is a general lemma. So this is, I think, in 2002. It says that if you have such a if you define something like this coset leader, actually you don't have to define the coset leader graph. You just have to define the coset leaders for this lemma to state this lemma. It says the size of C is always going to be less than this, where tau is exactly this MRW radius that you see there is this first MRW bound. This holds only for linear code because you cannot define the dual code for general non.
But
you can
give bounds better than MRW?
No. This will basically this cannot for general code. This cannot, but you see potentially you could have, because it's so what is being done here is that they said that set of all coset leaders of weight less than tau n, that number has to be less than set of all vectors of weight less than.
It can be much smaller in some cases, right?
In some cases, but asymptotically there is no improvement. In some, yeah.
What did they use it on? They use it on.
So they don't use. They just show that by so you get this lemma, which means that this is the fast MRW bound for linear codes can be derived as a special case of this generalized Alon-Bopana type theorems that they.
So it's stronger than MRW.
It could potentially. Potentially.
There are few coset leaders.
Right. If there are any fewer, like exponent, yeah. So for LDPC, so what Iceland and Samonosky showed is that they're like exponentially smaller number of coset leader than this all possible vectors of size, and that's how they get improvement. And that's exactly what we do. We just count the number of coset leaders and with those two properties.
You have few coset leaders because they have just size R plus 1.
They have these two properties that the size they will have this R plus low weight rows in the parity check matrix, and they cover. So you can count how many. So and that gives you a slight improvement over this shortening bound. So
if I'm not mistaken, Iceland and Samonosky put some paper on ECCC today.
Today?
This morning.
Okay.
Well, they talk about I just quickly looked at the abstract now, like half an hour ago, saying it refers to this coset leader graph that I never heard about. They refer to the discretized Ricci curvature of something. So
Okay. I will.
okay. Yeah, it seems like they anticipated your topic.
Right. Okay. Good. So why is this generally? Probably it's a little bit of digression, but like let me tell you like some intuition behind this, like for just a minute before, because I was planning to tell you a lot more regarding how. Okay, so this is why how is this bound form? So in this, if you look at this coset leader graph, it turns out that the eigenvalues of this coset leader graph will exactly give you the location of the spectrum, like where the code has non-zero number of code words. So what happens is, in this coset leader graph, so what is the large? If you look at the coset leader graph, the largest eigenvalue is n, right? What is the second largest eigenvalue? It turns out that second largest eigenvalue is n minus 2 d min. Not only that, if you look at n minus lambda I divided by 2, these are actually the location of.
If you can lift the.
Yeah. Yeah. So I was telling nothing, but n minus lambda I by 2, these are the location of the non-zero values of the code words. So this apparently is a folk theorem, and so Friedman and Tillich says this is a folk theorem. So and they give a reference from 91. So but this, I don't know whether this is well known or not, but that was the main intuition behind this bound, that if you have a coset leader graph, the second eigenvalue basically tells you what the minimum distance is, and then.
What of the other?
What did you say?
So I'm saying that you look at this coset leader graph and their eigenvalues, say lambda 1, lambda 2, up to lambda I. It says that if you look at the weight distribution of the code, right? You know that there is one code word at weight 0, right? Then there is a number of code words, I don't know how many, but at this d min, and then some at some weight. So this eigenvalues of this graph is going to give you these points. So for example, this n gives you n minus n over 2. So at 0, you know there is a location. The second one gives you d min the same way, and so on.
So just the support of the weight.
Just the support of the weight distribution are given by the eigenvalues in this way. So that was one of the main ingredient. And then Alon-Bopana theorem just says that lambda 2 cannot be very far from lambda 1, right? So that means the minimum distance cannot be very far from the 0, right? Because this is n minus lambda, so minimum distance cannot be very far from 0. So they generalize the Alon-Bopana theorem, and then that's the main idea of getting the bound. Okay, so that's a bit of digression, but so that was. Now I have to start erasing. Maybe, yeah.
It's always divided by 2. So with n minus lambda I divided by 2.
Yes.
So it's doubling.
Yes. So now let me tell you like the counting process. So basically, so I'm just using this as a lemma and count the set of all coset leaders of weight less than tau n. So at least for the case of when we have disjoint recovery set, this count is not that difficult to do, because you know that you are counting all vectors x such that weight of x is less than equal to tau n, where tau is given by that. And then the second thing, you know that since it is disjoint, you have this blocks of size r plus 1 in your parity check menu. So these are valid code words of the dual code. So only this first, suppose this r plus 1 is there. So then you have, since they are disjoint, you have this being non-zero. Now look at the intersection of the support of x.
Wait, why do you know that they are disjoint? This was all
No. No, I don't know. So I'm assuming. Okay, so the reason is that the way I proved this GV achievability over here.
Yeah.
Okay. Just no.
In the box.
Yeah, that's fine. Yeah, I just. So the way I proved over here, the proof that we showed, this is also assuming disjoint. So I'm even assuming this, if we can close in the construction. So if I by so no one told me that it has to be disjoint, but if by assuming disjoint I can close this gap, that would be something. But we still cannot. So I think there is serious. Like I think it's open. It's not like a lot of people tried to solve this problem. It's just like a few. So, but if you look at it, there might be other technique, like if some brains are. So why is this? So I'm saying for disjoint recovery set, the count is easy to do because you are just counting all the vectors of length less than equal to size width less than equal to tau n, and the support of x intersection with any recovery set, say Ri, which denotes this. The size of this has to be less than equal to why would that be true? So less than r plus 1 by 2. So basically I'm counting all x's of weight at most tau n such that if you restrict them to the first r plus 1 coordinate, you have at most r plus 1 over 2 once, the second r plus 2 1. So this is really easy counting. So how many such sequences can be there, and then you can just plug it in over here, right, to get the bound. So that gives you some bound. And this will be true because if this is greater, if you just add with x this r plus 1, so r plus 1 is a code word and x is a coset. We are counting coset leaders. You will get another vector in that coset, but that will have a smaller weight. So x cannot be a coset leader. So this is a really simple argument, and this takes you somewhere over. So it takes you somewhere over here with disjoint. Slightly improvement. So all these are I consider them like slight improvement, but these are special cases. For linear, basically the improvement is not visible in the curve. It's like 10 to the power minus 7 or something like that order improvement. So this is a little better because you can see this. Okay. So there are many open questions, and this is the status of locally repairable codes in terms of bounds. Now, there is one other interesting open problem in this realm of locally repairable codes that I think is worth mentioning. So information theorists are also concerned with achieving capacity, right? So this is we are talking about only minimum distance of a code. But suppose you have a locally repairable code and you want to know, since these properties, as we have established at the very first start of the talk, these are sort of different things. Distance and locality, we're not looking at them together. So we can just ask, okay, can a locally repairable codes with locality R achieve capacity? So in capacity, so we need to so basically we are sending them over channels of this kind. So we are using these code words to send think this is redundant, but I will just. So this is the binary symmetric channel where each bits can be flipped with probability p. It will remain same with probability 1 minus p. We can have also the binary erasure channel. So each bit can be erased. So then each bit can be erased with probability p. It's known that the capacity of this channel is 1 minus hp. Capacity of this channel is 1 minus p. That means if the rate of the code is anything less than 1 minus hp, then the probability of reconstruction. So suppose you have a maximum likelihood decoder over here. So whatever you receive, there is a maximum likelihood decoder that tells you which code, the nearest neighbor. So in this case, the ML decoder is just nearest neighbor, and here it's something similar. Then we want that probability of error averaged over all code words to go to 0. If your rate is anything less than that, that is possible to do. So that's the capacity. Now I'm saying, okay, no, I'm restricting myself not to all possible codes because, well, Shannon showed, and then like many users. So if you allow yourself to get any code, then you can just randomly pick a code that will have this property. But now I'm saying not any code. I can pick only a code that has locality r. So its rate is this, and locality r. Would it still have probability of error going to 0? And the thing is that for BSC, this question is, this is open. I mean, we don't know. But for BEC, there is actually, again, this shortening type argument that helps us prove this. So I will just tell you the argument for BEC, which is really simple. We can do it in 5 minutes. But then the surprising thing is that we are, at least I don't know if anyone else have looked at this problem. It's not that simple to extend this to BSC.
So what you're saying is that making it repairable is not a restriction? Or,
it is a restriction. So I will show the following result.
Yeah.
I will show that it's the gap to capacity result. So if you allow me 1 minus p minus epsilon, I cannot have a local repairability better than order of log 1 over epsilon.
So that
R has to be omega of log 1 over epsilon if your epsilon far from capacity, and this is also achievable. So you can so this is actually theta, that's possible, but here I don't have that thing.
But this is still a worst case locality.
It's still the worst case locality. So it turns out that
you could also ask, what if I want to have a probabilistic, like a few times
you can ask, and I don't know if anything changes over here. For the I don't know if anything changes.
Because given that you will anyway make errors in decoding some code words with small probability, why not allowing to do that?
No, it actually makes sense to think of it as worst case. I mean, you have n servers or whatever this is sitting on. Probably I mean, these guys make, lose information a zillion times a day.
Right.
Probably uniformly over all of them.
So
you
actually,
don't want, it makes sense that the R will be a fixed bound.
so if you remember the way those bounds, those converse bounds, for the case of at least when you have this distance thing, the way this bound is proved, so it doesn't matter if you have just a over average locality. Suppose locality for different symbols is different, and now you are just looking at the average locality. You can basically prove the same bound, and then all of for the achievability result, you assume all of them has equal locality. That doesn't restrict yourself. But here, instead of, suppose you're saying that different codes have symbols have different locality, you can just instead of just pick this t coordinates randomly, and then just say that, okay, on average they will have this locality, and this arguments I think would go through, and you will still have the same bound. And then whenever you are achieving this bound, you should be fine. I am not so sure about this case with this, but I think that you will basically get a similar result in terms of average locality. So the average locality has to be at least this. So let me give you a proof of that this fact over here. And then in the remaining time, I'll talk. I will tell you, like, that there are two other topics that I have wrote down here. Like, I didn't plan to elaborate a lot on them, but I will tell you what they mean. So, so you have, suppose you transmit this code word over a binary erasure channel, and now some of the coordinates are being erased. Okay. Now, what is the probability that a coordinate is not erased, as well as the recovery set of that coordinate is also not erased? So that probability, so for any, so ith coordinate not erased, and Ri is also not erased. So yeah. So the idea is exactly like that shortening bound. So now suppose I is the set of erased coordinate, the set of so I bar is the set of non-erased coordinate. So when I have a decoder, the output of this channel, I'll look at this I bar and then try to get back to the code word. Right? So it must have enough information so that I can get back to the code word. Again, assume that the rate of the code is R. So the size of the code is that we are considering is 2 to the power n R. Now, let me look at this quantity, which is h of x of I bar. So, okay, so what do I? Yeah, I don't want to introduce h. Okay, so log of c of I bar. So I'm basically looking at the code that is and the projection of the code on the set of non-erased coordinates, and seeing what is the cardinality of that set, what is the log cardinality of that set. So it would be n minus I. Now you see there are certain coordinates which are not erased, and their recovery sets are also not erased. So those coordinates are kind of redundant, right? Because you can recover them by looking at their recovery set, which are also non-erased. So whatever is the number of such coordinates, that I can just subtract from here. So let's say this is star or something, right? So what would be average of log of c I prime? This is going to be n minus np, because the average size of this is np. And what is so minus n times 1 minus p to the power r plus 1, exactly like the shortening type of case, right? On the other hand, I mean, it's easy to see if you represent it like this, but this log of c I prime, this is a random variable, and you see this is actually like a one Lipschitz function of the coordinates that are being erased. I mean, if you just change one of the coordinates, this thing would not change by more than 1. So you can use this like McDiarmid's like with Azuma's inequality, basically. So show the probability that this thing is greater than n minus np minus, so sorry, this is It will be less than equal to this because I don't really know. So we are in the right direction. That's what matters. 1 minus p r plus 1 plus epsilon is less than equals to e to the power minus n epsilon square by 2. I think this, so this constant might be a little off, but anyway, something like this. Let me write C, where C is a positive constant. Right, now I choose R to be less than minus 1 log of 1 over 3 epsilon divided by log of 1 over 1 minus p. So p is a positive constant, the erasure probability. So if I choose R to be anything less than this, then I just show that probability of log of
The rate is 1 minus p minus epsilon.
right, yeah. So Ci prime is greater than n minus np minus 2 epsilon. This is exponentially going to 0. Cn epsilon square. Great. Yes, you're exactly right. So with high probability, this log of C, so the whatever is the number of code. So again, you can see like in the case of the shortening bound, I mean the idea is basically the same. So you have, so whatever are the coordinates that are remaining, the number of code words that are supported over that is, so that is actually with high probability less than 2 to the power n times 1 minus p minus 2 epsilon. But you see, if this R is anything like 1 minus p minus epsilon, then there are like 2 to the power n epsilon coordinate code words that will be mapped to the same prefix, and your decoder would, the maximum likelihood decoder has no way to differentiate between them. So that the best probability, the probability of error is going to be 2 to the power n epsilon. And this happens with probability, with very high probability. Right? So what is this? So sorry, this minus 1. So basically R has to be, therefore, if it is with that rate, if you want to achieve capacity, R has to be order of log 1 over epsilon. And this argument cannot be extended here for the obvious reason, but there should be something simple, some nice argument, like clean argument like this that should give the same result over here.
So the
and
linear
maybe
dependence, so for erasure, it's linear dependence that the recovery set gives you can directly be translated into this bound on the log of Ci, right? This you still get for, because linear dependence for the BSC doesn't tell us much about how it can correct.
what do you mean by linear dependence?
What you wrote for the expectation of the log of the Ci.
Right.
Do you have such a thing for the BSC?
No, because for BSC I cannot isolate this this set of coordinates, right? So how I mean, it's not only that. I think the problem, so I cannot even write the first step, since at the decoder I have to just from a erroneous, like there is yeah, so the technique sort of fails from the very first step. Here I'm assuming that, okay, I can see this so the coordinates that I'm seeing is correct. I just have to make a decision. Yes. I think I have exhausted my time, but can I take like 2-3 minutes more to just wrap this up and tell you a few? Okay, so there is like this open, and I think one of the reasons these questions are open is that not many people, like in both of the cases, I think not many people have looked into them. Especially from TCS, very few people have looked, apart from just introducing the problem. there is not many work. But then this should be, there should be a similar result over here. It's not like yeah. Anyway, so that's open. So I will just take 5 minutes to talk about the 2 other topics that I wrote. So one thing is that this local repairability can be extended towards the case where you have your recovery sets specified, and that basically reduced to having local repairability over a graph, and you can define something called a graph, something called a storage capacity. So suppose you are given a graph, 2, 3, 4, 5. So you are given a graph and you store one symbol in each of the vertices of the graph. So x1, x2, x3, x4, x5. And now you are asking that, okay, so you can store potentially 2 to the power, like 5 bits of information in this graph. But now you have the constraint that if you lose any of the bits, you can figure them out from your neighbors. Why neighbors? Because it's a distributed storage system. You don't want to go very far. So just one-hop neighbors. Then what is the amount of information that you can store? So that's a well-defined so it can be a directed graph, which probably makes more sense, but let's restrict ourselves to this case. Then what is the maximum amount of information that you can store in this graph? And again, this depends on the size of the alphabet. So we call this the storage capacity of the graph. It can be generalized by saying that, okay, so you want to maximize entropy of x1 up to xn, where n is the number of vertices in the graph, such that h of xi given x restricted to the neighbors of I is 0 for all I belongs to V. Size of V is on the field. So suppose each xi belongs to some, say, fq. Right. So this is a well-defined quantity, and we can show that. So it's not difficult to see that it's upper bounded by the vertex cover of the graph. So it's something like a vertex cover. The reason is that if you have an independent set of the graph, then just by looking at the outside variables, you can deduce what they are, because there is no edges between them, right? So the amount of information that you can store here can be at most n minus size of the independent set, but n minus size of the max independent set is the vertex cover. So it is vertex cover is an upper bound. A lower bound can be given by a matching, right? Because you can just find a matching in the graph and then store one symbol, repeat one symbol in either edge, either ends of the edge in that matching, and then you will so this quantity is sandwiched between matching, max matching, and minimum vertex cover, but those two quantities are within a factor of 2 apart. So we kind of narrow it down to a factor of 2, but we cannot say anything more about this quantity for general graphs. So for planar graph, we can have a 3/2 approximation. Like for special graph families, you can have better and better approximation.
This is like an algorithm to compute the capacity?
Yeah, so the algorithms are like, we want to come up with algorithm, because of course you can if you don't have any time restriction, you can just enumerate all of the vectors. So there is also one other fine point here. So suppose you can define this capacity over any alphabet size q, and then you can then make q go to infinity, and this goes to an absolute value.
Log.
So your capacity, normalized by log. So if you are writing in bits, then you have to normalize by log of q. Right, and if you are Or you can, in other words, you can have the entropies HQ here. In that case, you don't have to. So this goes to some fixed capacity, and so then you don't even know what is the computational class, this thing. So you cannot just enumerate over this. So it's unknown at this point. And for planar graph, we have only, so for if you fix the, I'm saying planar graph because most of the algorithms for this vertex cover or like independent set, you have pitas for planar graphs. So you can have pitas for them when Q is fixed. But when Q is not fixed, you don't know, you don't have pitas, so you have only very loose bounds. So that's, I think that's a pretty ripe area, and it's not that I'm an expert on graph algorithm, but if someone sees this, they would be like there are many open problems. The reason this is interesting is that it has some connection with Shannon capacity of graph via something called index coding. So the last thing I would do.
Maybe we'll, you tell us about index coding at lunch.
Yeah, maybe I should do that in lunch. But this is what it is. Thank you very much for listening to this.